All right, let's just launch into this. Come on, there we go. All right, so I'm going to cover kind of an overview about powering the solar car. We're going to talk about some array background choices. We're going to talk about power tractors, DC-DC converters, electric motors and controllers. Then I'm going to move on into some more general electrical stuff, and then I'm going to move on into everything else. And this is a kind of quick and a little bit more of a high-level overview meant to be an introduction for newer teams. Those that have done this before might find that some of it's pretty familiar. Maybe one or two things will still be a little bit new. Let's talk about arrays. There's a lot of different things you want to consider with an array type. The first thing I'm going to talk about is the substrate and the support frame. I've got a couple of different things here. Obviously, most of these things would be common sense, but you don't necessarily realize it until after you've done it. One of the main considerations that you want to have for whatever supporting your array is rigidity. You don't want, because we're going to have often large overhead arrays like this, and notice that there's struts coming up to the back to support it. It's because you don't want things to fold, break, flex, and if you have a non-prefabricated panel, if you made your own, again, speaking from personal experience, 20 plus years ago, you want to have something rigid underneath it. Otherwise, you bend and break connections between the solar cells or solar cells themselves. Second thing you want to consider, and these are kind of a toss-up, weight and cooling. Obviously, you don't need to necessarily build a tank to support it. And there is an efficiency curve for heat and solar cells. So I think it's on the next slide. Also, finally, conductivity. If, again, you have bare cells, you don't necessarily want to lay them down on a conductive surface. That would be bad, because you're dealing with quite a bit of power that's there. So these are just things to think about as you're considering how to design your array. I'll get into more in a second. So one thing that I wanted to point out, solar cells, and I put a link to where I pulled this. This is a guy who just did this on his own, and this was his roof panels on his house. But he put on their manufacturer kind of efficiency and what he actually calculated based on a year's worth of data that he got. Essentially, when the panels get above a certain temperature, you start to see a drop off in efficiency in the panels or in the cells. So if you're completely sealing up your cells, there's no airflow, there's no cooling, you may be one of those people that in the Texas sun in the middle of July are starting to fall off this curve because your panels are actually starting to get quite hot. So just one of those things to be aware of. Let's talk about shapes of arrays. So the most common thing, and I know I'm pulling iron lines in here, but I still consider this essentially a flat array. They're a little bit easier to execute. You don't have some of the sun angle concerns that you do with a curved array, because once light becomes, let's call it more than like 15 to 20 degrees off of perpendicular to the solar cell, you find that you get a very significant drop off in the power that you get from it. Some of the newer cells might be better at off-angle light, collecting and gathering it, but typical solar cells have that fall off. The second thing you need to consider that I also want to show here is the wing over body design, or if you want to have a canopy above array. The drawback to a canopy over the array is you potentially have some situations where your canopy is actually going to be shading these cells over here. So you want to consider that when you break up your zones, because the solar cell that's the least performer is going to define the performance of the entire zone of solar cells. So that's just something to think about. The advantage of an over body design is that you don't have that. You've just got the flat panel. However, you can see that when you condense it down like this, it does offer some better opportunities for aerodynamics, because you don't have struts and things sticking out here causing more drag. So, you know, just trade-offs with some of the flat arrays. Curved arrays. This is Staten Island's car. So this is, you know, one of the more classic things that we've kind of seen. I threw up the picture from last year's race, the team photo, just because I wanted to show it's kind of interesting. that the majority of the teams in this event have kind of chosen to move away from the curved array design. It's not necessarily that there's anything bad with a curved array design. Again, it's taking advantage of all the surface area you have when you're trying to build the most aerodynamic car that you can. And I think our new cruiser division even kind of encourages that kind of placement versus trying just to have solar cells on the very top of the car. So let's move into panels. There's what I'm going to call pre-made commercial panels, which are pretty easy to find these days. They're all over the place. Solar in the last 10 years has exploded in popularity because of all the use on roofs and at home. These panels, what I'm going to call commercial panels, are typically made for roof installations. They're heavy. They're typically heavy. They're made to sit on a roof. They're not really thinking about considerations for putting on your solar car. So something to be aware of if you're just going to go buy any panel that's out there, you may want to take a look at the weight. One of the advantages, though, of the heavier panels is they tend to be pretty rigid and pretty easy to mount, so you don't have to have a lot of structure to support them. However, there are pre-made lightweight options out there too. SBM Solar was one of the companies, I want to say the Minnesota team. No, the Minnesota team made their own array. I'm not sure which team it was that was using these prefab panels. But SBM Solar sells thin prefabricated panels like this. SunPower actually has some stuff, and there's a ton of other ones out there. I mean, in 10 minutes of Googling, you can find yourself at least 5 different options and a variety of places to buy them from. So just to be aware, if you look, there are alternatives to just kind of the standard, I'm going to plaster this on the roof. And typically these have like RV or marine applications where you want something thinner, lighter, or even flexible. Raw cells and lamination. So this is something that you have to plan way ahead of time. And I'm repurposing some of Mark Westlake's presentation on this, so I'm not going to take credit for it all. But he's right in the note that if you're going to try and start doing a solar array from scratch, raw cells, you may already be too late if you're targeting this year's race, because it is just an intensive and kind of expensive process. You can build the most lightweight panel that's possible because you're individually building up the cells and affixing them directly to your car. And you can maximize power and minimize the aerodynamic drag, but it is a lot of work to do that. One point that I want to mention out here, there are companies like SunCat, and I know we've got a few folks that are part of our solar family that have contact with them over there. They're one of the main people that do kind of custom encapsulations for solar cars. I think SunCat was the person that did the encapsulation on these cells here for the Staten Island team. So just a comment about that. So again, this is the Winston car, one of the former Winston cars. They went a route where they had individual panels made and laminated that they could Velcro down and easily remove on this car, versus what you see for the Staten Island car over here, where it's more permanently affixed. But both of these are bare cells that have been laminated and built up. The do-it-yourself experience, I can say from back when we did this, because we built our own arrays all 3 years, it is a pretty amazing learning experience. You're going to get some great soldering skills out of it. The learning curve is pretty steep. I don't know how many cells we destroyed, but it's like working with potato chips. It can be harder to find raw cells these days, and it takes a lot of manpower and planning. Yeah, from a sponsor perspective, it's really hard to watch. And actually from a team perspective, when you know how much those cost and what you had to do to fundraise, it's hard to watch your cells continually breaking when you're doing your best to install them. But you can get the exact fit for your car. So this is going to be some of the photos from the Minnesota team. Upper left here, you can see one of the students actually soldering the leads onto the cells and then putting the cells into small groups like they're doing. So there's a couple step process. You can see he's got a soldering iron, he's got all his leads set up here. They're special solder paste that you're going to be using for this. And again, you get very good at this over time. But you can imagine that in order to get to this point, there's a lot of this that you're doing, and this isn't a quick soldering process. Here's one of the drawbacks. When you break a cell that you've got already in place, the only thing you can do, or if you miswire it, is to finish breaking it up, vacuum it up with a vacuum, and then very carefully try and reconnect the leads and drop a new cell on top of that. Likewise, if a cell is damaged during the race, this is the only thing you can do, or you can basically try and bypass the cell by doing a jumper. But it gets to be frustrating when that keeps happening. All right, I'm going to move on to power trackers, or MPPTs, maximum point power trackers. Here's the thing. Solar arrays, it's not just as easy as taking the 2 wires off the array and hooking them up to your batteries. Could you do that? Yes, but you're not going to like the results. Voltage from your solar array needs to match, this is why, voltage from your solar array needs to match that of the battery pack. You don't want an array that's outputting 130 volts for a 48 volt system. That's just not going to end well. More often than not, when you kind of break up your solar cells into groups, because remember, the lowest performing solar cell, if I shade one cell in a group of cells, it's going to drag down the performance of all of them. So typically you want to make logical groupings so that if you get one corner of your array shaded, it doesn't affect the performance of the entire array. And those are what we typically call zones. So the groups or zones of solar panels won't match your system pack voltage. They just typically don't. It's too hard to get the exact right number of cells to add that up. And even if you do match the voltage, I've got a 48 volt panel, I've got a 48 volt battery, I should be good, right? Not really, because it's not going to be efficient for as you draw your batteries down, or if you charge them up for putting power into there. Battery chargers don't just output a fixed voltage, charge your batteries. It scales and changes as the amount of charge on the battery scales and changes. The other thing is there, without any protection at all, if you put your solar panels in the dark, you can actually have reverse current flow into the panels, which can cause a fire. All these things are taken care of by power trackers and, well, DC to DC converters. I think you're more common to find the terminology as being MPPTs. A DC-DC converter can be something else that's not necessarily intended for charging of a battery pack versus an MPPT. So what do they actually do? So this is what you get from a power tracker. They're not only are they going to take care of the reverse voltage protection, but they're going to take whatever voltage you have and tailor it to whatever the ideal charging voltage is for your battery pack. And they're either going to be able to boost voltage, like I've got a low voltage panel that's only at 40 volts. I need 72 volts for my system. You can get ones that can boost like that, or you can buy versions of MPPTs that can buck, meaning I can put in 150 or 140 volts DC, and I can buck it down to 80 or 72 or whatever the value might be. They're also a main source for telemetry for your array. Most power trackers at this point have tons of telemetry that they want to spit out to you, and a variety of ways to tap into it, to pull it into your telemetry systems. Or you can just take their built-in displays and have that displayed to the driver. You still get a good idea of what's coming off of each of the zones of your array at any given time. The other thing to be aware of is when I talk about array zones again, so maybe I'm going to pick on the Winston car right now. Maybe because of this right here, they've got a front array, a middle array section, and a back array section. Those 3 sections would mean that they'd have to have 3 power trackers, one for each one of those, if they wanted to implement something like that. I think the Staten Island car either has 4 or 5 power trackers. Maybe it's just 3, I can't quite remember. But same thing, they've got multiple zones on their panel, so they take advantage because, you know, unless the sun's directly overhead, one side of the car is likely not going to be getting the same amount of power as the other side. So it makes sense to split it up. Anyways, the takeaway is you actually need power trackers for each one of those zones. You can't run multiple zones into a single power tracker. Otherwise, it just becomes one zone. So real quick, here's some of the more common choices that we've seen. I'm sure there are more out there that are more current than what I'm aware of right now, because when I raced, it was 20 years ago, and I'm kind of going off of some of the stuff that I see more often on solar cars. Back in the day, my team used the AERL trackers. They went away for a while and I believe came back and are now available again. I don't know how well they compare to some of the other ones out there. Solar Converters is another company. Outback is a very common one that we see at the race. And Jenison is one that was mentioned here, but that's kind of a new one to me. Again, I want to clarify a little bit too, that even though I mentioned DC to DC converters up here, you really want to look for a power tracker, something that's meant to use with the solar array charging batteries, not simply something that converts one voltage to another. Here's what the AERLs look like. They always had the giant blue capacitors on top of them. Ours managed to hum. You could actually tell how much power you're getting by the frequency of the hum coming from the boards. Wasn't supposed to do that, but it was kind of cool. All right, so let's move on to some quick stuff on electric motors. Again, please feel free to stop me at any time if you have any questions. This is meant to be a high-level kind of primer, just as you wade into it. And I always want to say, too, that if you do have questions, you can't find help with something, feel free to email us. Even if it's something that it's not just, I want to do this, it's like, we're stuck here. We have no idea what we're doing. We can try and give you some help, or we can try and put you in touch with another team. You guys have also seen some of the great teams that are willing and totally happy with helping out other teams and building those connections. And we as event staff are happy to kind of help foster that connection. So if there's something you're really struggling with, even if we as staff are not the right people to answer, we can help you get in touch with somebody that can provide you some guidance. So a couple of types of things here. We've got two basic categories of DC electric motors, either brushed or brushless. I'm not going to go into the internal makeup of the motor. I'll leave that as an exercise. It's actually a pretty cool physics thing if you want to go look at it. But essentially, brushed are the more basic, lower efficiency but lower cost and kind of robust electric motors that we see here. Brushless, you can actually get to high efficiencies hub motors. The controllers can be a little bit more difficult to integrate with versus those with brush motors, and these tend to be a little bit finicky. They're also quite a bit more expensive. The trade-off, if you get it working, is you can get something in the mid to upper 90s in efficiency. I think the hub motors can get all the way up to like 98% efficient versus the brush motors, which are down in the upper 80s, like 88 to 90, depending on where you run them. Here's a couple of examples. This is, you've got like the Briggs and Stratton, the Lynch. Back when we do this in person, we sometimes have these motors laid out on the table. These are kind of just some of the common things. Like you have the PMG 132, which has a really broad range, 12 to 72 volts that you can run it. It's about 24 pounds, $1,400, which isn't too bad these days, and it'll achieve the 90% efficiency on it. Again, all of these are pretty common motors that we see. One thing I would recommend that you look into is consider the weight of your car. You do not necessarily need a 25 horsepower electric motor to push your 800-pound car. Likewise, you don't necessarily want to go with a 2-horse peak electric motor for your 800-pound car, because you will be unhappy with the results the first time you come up to a hill. So just think about that. Typical range is, I think, I want to say 10 to like maybe 18 horsepower peak. Somewhere in there is what I commonly see for solar cars. If you're going to be a little bit heavier for your first car, you're going to do it out of mild steel, you don't know, just go with a little bit higher horsepower motor. Yes, it'll weigh a little bit more, but then you know you don't have to worry about it. telling you, you do not need a 40 horse motor to push even a 1200 horsepower or 1200 pound solar car. Okay, so here, and this is a little bit hard for me to read positioned further away from the laptop, I want to throw up a couple of motor efficiency curves because these things confuse the heck out of people. Basically, how you generate this is you take a motor and you start running it while you collect data, and then you start putting load, in this case in inch pounds, on the shaft. And we can see here, I'm going to scoot a little bit closer. RPM is this little dash line. This is at 24 volts. This is the same motor. This is an ME0909. We can see when we've got no load on it, the RPM is somewhere around, 2250, we'll call it. As we put more and more load on it, it starts dragging down to about 1800. At the same time, we see our current, which is the red line. This was basically no amps because we're free spinning, all of a sudden shoot up higher and higher. When I want to read how many amps this is, I look at the amp scale. When I want to read what RPM I'm at, I look at the RPM line and the RPM scale. One of the cool things I want you to realize is this is the same motor at 24 volts versus 48 volts. Here's the RPM line down here for 24 volts. When I double the voltage on it, all of a sudden my RPM is higher up here. Now, how does this help me? I can take away from this squiggly line up here is the efficiency of the motor. And basically what this tells me is I can see, let's see, where's efficiency? Efficiency is over here. So this line right here represents 90% efficiency. Well, look at that. I'm running about 90% efficient from here to here. Well, what RPM ranges does that correspond to? So I just draw a vertical line. See, it falls off somewhere around here. So let me go back, and there's the RPM line, which corresponds to about 2000 RPM. And over here, I started to get efficient at, let me draw a vertical line, maybe 2150, 2100, somewhere in there. So it tells me that at 24 volts, if I want to operate in my peak efficiency zone for my motor, that I want to be between 2150 and whatever we said here, I can't remember, 2000 or a little bit less. And if I scale that up to 48 volts, look, the curve changes. Now my peak efficiency is somewhere between here and here, and that corresponds to, again, here's the dashed RPM line. I'm going to go down and look, that puts me at like 4,400 RPM. And then let's see, we fall off somewhere around here, I'll call it, down to like 4,100. So if I'm running 48 volts for an ME909, and I want to be as efficient as I can, I want to target my cruise speed to be between 4,400 RPM or whatever we said in 4,100 RPM. And then again, that's the most useful thing that you can take away from this. There's other things you can look at too, peak power, stuff like that. But I think for the purposes of, well, okay, I've got this motor. I know that it's got a broad range of RPM. What should I actually be running it at? How am I going to gear it? That's where this comes into play. And you could have just made 6 separate graphs, but when we talk efficiency of motors, somebody a long time ago decided that, well, let's just overlay all this data on one plot and make it so you can look at anything anyway, which sometimes makes it a bit more confusing. Yes. So Robert, this is a newer version of the PowerPoint. William's already answering it. Yeah, we'll put the new version up there. This is different from what's on the website right now. Let's see. So here's again, here's the ME909 that we were just looking at the efficiency curves for. It's 24 pounds. It's a good replacement for the ETEK or the old Brices and Strattons. It's $500. You can't really kind of beat that when you're looking at something that's kind of robust and low cost. Here's the advanced DC. We ran an advanced DC motor. Again, this is actually slightly larger than I think the one that we ran. Ours was, I want to say, 12 horse peak, and our first car was, I want to say, in the 800-pound range, and we had plenty of torque and plenty of ability to go up hills with that. Here's a brushless motor. This is the ME0907 brushless. So you can get above the 90% efficiency. According to when this package was first put together, it's around $460 for the cost of it. But again, you need a more specialized controller if you're going to be doing a brushless configuration. The place you go to buy the motor will often give you the recommendation if this is the controller you should pair with it. And then there's the hub motors, the NGMs, or now the Mitsubas that are taking them over. NGMs really aren't around that much anymore. Some of the legacy teams still have them. But regardless, the takeaway from this is you can get amazing efficiency. You do have to be able to, and the most effective teams have found a way to adjust the air gap in real time. That's kind of been the secret there, so that whatever speed you're traveling at, you're always running at peak efficiency with this. But you're looking at a $25,000 investment, and we've had multiple years where somebody's blown a motor or blown a controller. Hub motors just aren't super robust compared to, you know, even the more typical brushless or brushed motors. These you really can't hurt. You can try, but you typically can't hurt them. Brush controller, pretty common. The Ultrax Axe. They often are operated just by a 0 to 5K potentiometer. That's your throttle pedal, or on the track. You can substitute it and switch it out with a 0 to 5K potentiometer and do cruise control. Nowadays, they're programmable, so you can do all sorts of cool curves. You can set your peak current draw, so it limits the max output to the motor, things like that. There's all sorts of things you can do with them, and these are not super expensive. And this was just a picture of a Sevcon controller that you can use with a brushless motor. Again, these are ones that you're going to program. There's a lot of different things that are going to go into them. And if you do buy a brushless motor, whoever you buy it from, the EV store will give you a strong recommendation of what controller to pair with it. And then you can work that on your own for finding the best or the documentation for it. How much does a controller for a brushless motor cost? I don't know. You can go to Cloud EV or another one of the places up there. I want to say, well, I don't want to say it because I didn't look recently. You should be able to get a brushed motor controller between, you know, like $500 and $1,200. So I don't know how much it would be for a specific brushless controller, but I mean, even if you Google it on your phone, you can go look at some of the major EV sites. And we do have links to those on the website, kind of in the white paper section.
So one of the options that you can get for a brushless motor is the Sevcon motor controller, and they're on the order of about $600.
Okay. Thanks, William. All right. So, brief interlude on gearing. We talked about motors. I showed you efficiency curves. But how does that all relate to what I'm going to be doing? Well, you want to gear your car for a reasonable operating speed to begin with. Unless you look at the race day, and once you've got the route, you can do it. You can look it up from a topographical perspective, and you can see what the altitude gain and the altitude drop is. Unless you've got a race day where you're dropping 5,000 feet over the course of the entire route, you certainly don't want to gear a car for like 50 as your operating speed if more often than not you're going to be driving at 25. So just be realistic about it, because what's going to happen is if your gearing is way off, it means that if you're traveling much slower than that, you're going to be in the non-efficient range on your motor. You're not going to have a whole lot of power when you try and climb a hill. And it's just not going to lead to a great situation. So be realistic, and this is where testing comes in. You always want to have multiple sets of gears that you can swap out, because you may not know the best. But a good starting point is in the 25 to 30 mile an hour range to see where you're at. And for a first year team, that might be a little bit high. Remember, we do have a 15 mile an hour minimum speed though. So the minimum I try and shoot for is probably 20. But again, I leave it to you guys, and this is why testing is so important. There was a note here from Mark, and I agree with this. Chain drive systems can be very efficient if the gears are aligned and lubricated, and the chain's lubricated. That's absolutely true. I honestly don't have a problem with chains or with belts. There's pros and cons to both. If you do get a belt drive setup, though, be sure you actually get a belt that's meant for transmitting power and not a timing belt. A belt for transmitting power has rounded teeth, not square teeth. Square teeth will leave you disappointed the first time you try and climb a hill. And then here it says there's a 48-volt system with a 15-tooth front on the motor and a 70-tooth on the rear with a max speed of 36. Well, how do you get that all figured out? Here you go. I'm going to give it out to you. Your speed in miles per hour is 60 times the motor RPM times the teeth on the small sprocket times pi times your diameter of the wheel in inches over the teeth on the big sprocket times 5,280 times 12. You should double check my math. I did this at about 11 o'clock last night, and this isn't the most useful form of this formula, but you should be able to figure out how I got to this point and manipulate it for yourself. And again, this is assuming a big sprocket on your drive wheel that's this term right here, and a smaller sprocket on your motor and whatever target motor RPM you want to operate at. So here's a neat little takeaway formula for you. And again, I would break this apart. This is a great thing you can put to Excel. And if you go back and look at your efficiency curves and you know what wheel you're going to buy, you can start to figure out what gear ratios seem reasonable for you to run. This again is from Mark Westlake. There's a couple of places that he went to for custom sprockets. McMaster Kart, Ranger have some stuff too, but you can also find some stuff at like go-karting stores. But these places are also great because right here you can find a big variety of stuff at non-significant cost. So just stuff to check out. So there's a couple of nuggets in there. The electrical system. All right, how am I doing on time here? Not horrible. Okay, so here's a nice shot of the bulk of the propulsion system. There's one of those axe controllers right there. There's some power trackers up here, some high voltage cabling, some low voltage stuff running around in there. Anyways, electrical system all in one shot. Propulsion system is what's going to be driving your motor. You got to use the correct wire gauge for this. Otherwise, you're just going to burn things up. And again, I would expect that for most teams, if you got a really high voltage car, you're probably going to be in the 6 gauge range, maybe 8 gauge, but that's kind of starting to push it. If you're running 48 volts, 36 volts, I would expect that you'd be probably down in the 4 gauge range. And again, I don't really see, maybe if you're running 24 volts, you want to drop down to 2 gauge. But I'll leave it to you to figure out what's appropriate for your car. I'm going to mention that disconnect switches, they always need to be designed for DC. That's going to be a problem when you go look for most of your electrical components is AC versus DC ratings. DC ratings mean that they're meant to handle DC current, or like in the case of the switch, interrupt DC current versus AC. Fuses will have different characteristics for DC and AC as well. So in some cases, so you want to be careful about that. And fuses are an issue that we get into every year for the propulsion system. Your fuse should be sized for no more than 200% of what you expect your max draw to be. That doesn't mean what the maximum amps a current or your motor can pull is. It means what the most you expect to be pulling based on your testing. Because I could have a motor that can pull as much as 800 amps. That doesn't mean I should put a 1600 amp fuse in my car, because that's going to do absolutely nothing for you. More often than not, if you're at you're at low voltages, 24 volts, you may find that you're only pulling 80 to 100. So it would be much more appropriate to have 160 to 200 amp fuse, even though, yes, the motor can theoretically pull 800 amps. Otherwise, your fuse does nothing to protect you, and the thing that'll burn up will be your wires or some other component in your car versus the fuse that's designed to protect you. The auxiliary electrical system is everything else on your car that's not propulsion, lights, fan, horn, telemetry system, anything else. There's a lot of separate rules about that. And basically for the auxiliary system, you get free power. You can change out the battery as often as you want. The one thing is you do have to have a low voltage warning system that aggressively warns the driver, which I think I'll talk about in another slide or two. And electrical schematics, we're going to have another presentation on that in a little bit more detail about what amazing things you can do with some of the tools out there. But I wanted to show you that it doesn't always start out, you know, I'm one of those people that I want to draw things out on paper sometimes first when I'm rough sketching it. This is a very nice rough sketch. This one's really detailed, and you can see what they translated it into over here. But we do expect that you have a CAD drawing for your electrical diagram. And let me tell you, if it were me, I'd have about 20 copies of this printed out and around my garage, because every time I'm troubleshooting, every time I'm wiring, every time I'm doing something, I want to be able to reference this. And your electrical drawing should have adequate detail to tell you where that wire that you're working on is supposed to go. Batteries.
Just to chime in there, we will have a presentation on how to develop great electrical schematics right after this. So there's a way you can you can CAD up your electrical schematics.
Thank you, William. Yeah, that's why I just wanted to kind of touch at a high level. Okay. Batteries. Here's a little bit of a word of caution. They're one of the areas where you get what you pay for. You need to make decisions of what voltage your car is going to run at. Higher voltage means lower current. Why do you care? Lower current means heavier duty everything. Higher voltage means it's potentially more dangerous, especially when you're working with an energized system, which should hopefully be very rarely. You want to think about how much weight you want to carry. You want to think about how much energy you're going to get with that weight, because there are trade-offs. Even in the lead acid world, there are batteries that have a better storage capacity to weight ratio than others. You want to think about whether or not your solar panels can actually recharge the battery pack. If you go with the maximum 5 kilowatts, but your array, because it's a small array, is never going to be able to fill that up within a day, maybe you want to reconsider whether or not you actually go with a full 5 kilowatt battery pack, because once it's drained down at the start of the race, you're just carrying dead weight. And there are considerations whether it's a road race or a track race. We tend to have a lot more variability in conditions on a road race than we do in a track race. 5 kilowatt hour rule, we'll talk about that real quick. This is always at the 20-hour discharge rate. If your spec sheets don't have 20-hour discharge rate listed on there, you'll have to interpolate from what's available, because that's the exact same way that we're going to be checking it. For 12-volt, 84 amp hour batteries in series. And again, this is 84 amp hours at the 20-hour discharge rate. So it's 84 times 48 is 4,032 watt hours. Or 4.032 kilowatt hours. So again, for these 12-volt batteries, that's less than my maximum, which is 5 kilowatt hours, but that's still about a 230-pound battery pack. So again, this is something that you want to consider and decide, because it is a big trade-off. The weight for the amount of storage, unless you're in like the advanced division, in which case you can use lithium packs and you can get the same amount of capacity for, like, I don't know, 30 or 40 pounds, maybe less, maybe more. It's ridiculous. But here's where you are with lead acid. It's quite a bit of weight. Kuchert's number. This is an important number if when picking a battery for it describes the discharge characteristics of the battery. It's also important to know when you're programming any type of like link 10 meter or something like that that's going to monitor your battery capacity, because as the discharge rate increases, the usable capacity of the battery decreases. The closer you are to 1, the closer you are to an ideal battery, which would just be a straight line. But in reality, lead acid batteries, you're going to find yourself somewhere along this curve. Even though we had 80 amp hour batteries on our team, I found that our usable was closer to about 50 amp hours, just because of the rate which we discharged them. Testing batteries, you want to actually be able to test your batteries, and if you have the chance to do it, if you have a chance to buy more than the bare minimum for your car, it gives you an opportunity to cherry pick the best ones of the group. You also want to know that cycling your batteries is a good thing with lead acid, because after you cycle them a few times, you kind of break them in, you'll actually find the capacity increasing. You do want to be recording the telemetry though as you discharge your batteries, because otherwise you kind of wasted a lot of time sitting there. And this is again the Minnesota team. They're using incandescent light bulbs. This won't work with LED lights. You'll be there for weeks. Incandescent light bulbs to drain down the batteries.
All right, just to chime in, as noted in the chat, when you look at capacity for lithium batteries, we do calculate that at the 1C or nominal rate. That's how we do the thing compared to lead acid.
Thank you, William. I totally forgot to put that in here. Okay, just a couple of battery options out there. So, all right, I'm running low on time. I'm going to try and get through this really quickly. Here's one of the common disconnects that we have now. Remember that relays are allowed now, and you're not allowed to have high voltage wiring in the cockpit anymore, which essentially forces you in the relay direction. Here's just a couple of links that you can go to for switches and fuses. I'm not going to spend too much time on that. We can talk about that over email. Low voltage indicators. Everybody always asks, well, what do we need for a low voltage system? Here's one COT solution, commercial off the shelf. That's $6. That's an audible, tunable, low voltage alarm for you to consider. The link's in there. Wire. I talked a little bit about this before, but use welding cable. Welding cable has more strands in it and tends to be much more flexible. I'll show you some of the proper crimping tools, things like that. Do be aware, there's a lot of stuff. This is different than it was 10, 15 years ago. There's a lot more stuff available on the internet these days, and there are counterfeit things out there. There are counterfeit wires. What does that mean? People trying to claim that it's a 4-gauge wire when they're actually putting 6 or 8 gauge in there to save on the copper and putting a thick jacket around it. Again, you can kind of see in this picture too, an example of 18 gauge wire. And again, on the right is the fake 18 gauge versus what a real 18 gauge is. And all they did was put more of a jacket around it. So buy from somebody reputable. I put a link down here from Flex Innovations, which is I'm not necessarily recommending them as a company, but they are one person that went out there and gave some recommendations on how to tell if the cable you're buying may be counterfeit, meaning that it's not what you thought you were getting. Auxiliary system wire. This is another place where it sometimes pays to invest a little bit more. More strands tend to be a better wire to work with because I can have 18 gauge wire with 7 strands, or the other common one is 19 strands. Let me tell you, 19 small wires versus 7 thicker wires. This one's a whole lot easier to work with. And then there are other options out there, but just to be aware of it, not all 18 gauge, 16 gauge, 20 gauge wire is the same. It actually varies by the strand count. Takeaway from this is check out welding cable. Welding cables are super flexible and great to work with to make battery cables out of. Heat shrink should always be used on this. You're going to want to get a heat gun. I recommend, again, 3M heat shrink is the pretty good stuff. It's in my opinion worth it. A heat gun, these things are low cost, 25 bucks, and crimp connectors. Basically, you don't want the ones with plastic. I'll show you what to do if you do have those. And I usually like working with the bare ones. You can do the same thing with your big battery cables. After you crimp them, you can slip some heat shrink over it so you don't have any loose conductors. If you're wondering what heat shrink is, it's just this. It's an insulating material that when you apply heat to it, it shrinks up and kind of forms fits whatever you're working on. Soldering, overviews of tools. You need wire strippers. You need solder. It would be really tough, in my opinion, to build a solar car without doing any soldering. 6040 tin rosin core solder is typical. There's variations on that with the amount of tin, the amount of lead. You can get lead-free solder, but it doesn't tend to wick quite as well as the 6040. I need to change this. Very small diameters, 0.6 millimeters, 0.8 millimeters. They're great for working like with a circuit board, not so great when you're soldering 16 gauge wire or 18 gauge wire. Larger diameters greater than 1.5 millimeters. I think what I've actually got here is 0.06 inches. I'll show you that in just a second here. I'm going to talk about irons versus guns. I actually wish I had more time for this. Basically, I strongly recommend soldering guns for doing wiring in a solar car. Soldering irons are great for if you're going to work on a circuit board. There's pros and cons to each, but guns are pretty amazing for doing quick jobs with larger wires. The most reliable wiring I've ever found in the solar car is taking crimp connectors, which I don't like just crimping them by themselves, because they're going to shake and sometimes you don't get a great crimp connection or something pulls loose. So on my team, what we do is we crimp them, then solder the crimp in, and then slip heat shrink over it, shrink it, and call it done. And those connections never failed. That's a permanent cable right there. So before I go on to live demo, are there any questions? Okay, let's switch gears for just a second here. So I've got 8 minutes to do a real-time demo. I've got some wire here that I'm going to be playing with. Like I said, I tend to use, and I hope you guys can see this okay, these kind of crimp connectors. I mean, I went to Amazon, I bought a whole box of them, so I just have stuff sitting around in my garage. But yes, they all come with these plastic jackets on them. So what I do is I just, drop my tools. I take pliers and just yank them off, because I've got to put on it, instead of that plastic jacket, I've got my nice assortment, although even though I recommended 3M, I have off-brand heat shrink. This wasn't expensive at all. This was maybe $6 or something. And I've got a wide variety of stuff covered here. Basic tools. I've got wire strippers. Some people like this kind of a wire stripper that's got all the gauges in there. I find them to actually be a little bit of frustrating to use versus just one of these kind, because I can actually cut the wire or I can just strip it. Just takes a little bit more practice. Clearly I'm rusty. My solder, here's kind of what I was talking about. I don't know how easy it is to see, but where did it go? Here is kind of the difference. You can see I've got very thin solder here, which works great if I want to take on a project. Like this morning I was playing with this where I was actually starting to solder it. Yes, I put it on there backwards, but I was trying to do soldering to a PCB board. I absolutely want thin stuff. This is 0.8 millimeters, super tiny. This is a little bit tiny even for my 16 gauge wire that I'm using right now. What I more prefer is something like this. This is 0.5 inches diameter from the old Radio Shack, which, sorry, you guys can't see that well because the light doesn't really exist anymore, but it's kind of my favorite to use. The reason why I want to talk about the soldering stuff is just because When I saw people working in the garage last year, it kind of shocked me that some people were struggling with this. Yes, I do keep some of these butt splices around for using like in emergencies on the road. I do them, but if I'm at a stop, if I'm in the garage, I'd always solder. These are the type of lugs that you'd see for your battery cables. These are smaller sizes than what you'll actually be using. What I wanted to point out is that when you go to crimp them, obviously you can't use a standard crimping tool. That would be kind of disastrous. What you do need to go get is actually a battery lug crimping tool. And the way that these work is you lift it up, you drop your crimp in here with your wire in there. Don't forget to put the heat shrink on it. And then you knock it once or twice with a heavy hammer. You don't need to beat the snot out of it. You just need to get it enough till you crimp it. Then you always want to pull on the wire afterwards and make sure it doesn't pop out of the connector. And that's how you make a battery cable, just very quickly. See, I've got my soldering iron here. I've just got an off-brand soldering iron. If you are going to use a soldering iron, important things to note, you want to keep the tip clean. This really shouldn't touch solder, and it really should be bright and shiny, not dull. Again, I would not use this for trying to do solar car wiring. If you are going to do PCB board work, you probably also want to get yourself some desoldering braid. There's also old desolder. This is old. There's also desoldering tools you can get that are basically air bulbs that when you get the solder liquid, it sucks it up into the bulb. Those can be handy too. This soldering gun is probably 40 years old, still works amazing. You just have to put a new tip in it every now and then. And again, why I like these is they get very hot very quickly. So I just pulled the trigger down right now, and let's see, it's only been a few seconds, and already I'm hot enough to melt solder. And within a few seconds of me putting it down and taking the heat off, it actually will be more or less cool to the touch. Important when you're working in the car and you forget that you set your soldering iron down and you go to reach for your soda and instead of find the tip of the soldering gun. This is less likely to burn you than that thing which is constantly hot. So I'm going to take just a minute here and let's talk about how you actually solder a wire. I know this is a quick demo, but here's what you want to do. And if I want to build a quick cable, I'm going to put these connectors on it, which hopefully fit. First, I'm going to strip off some wire. I don't want to just strip off a tiny little piece. So I want to get something long. See, sometimes it fans out a little bit like that. It's okay to just give it a little bit of twist. I'm going to then take, and the very next thing I'm going to do is tin it. This is a step that people don't realize if you're actually going to do soldering, is that you can save yourself a whole bunch of effort if you tin the wire ahead of time. Tinning it means wetting it with solder. So the first thing I'm going to do is I'm going to get the tip hot, get some solder on it, because the solder is actually what conducts the heat. Start a little bit on there, and then I move the tip underneath the wire. You can see it's almost tinned itself already. And that's it. Not a lot of effort to that. I didn't get a totally clean tip on that, but you can see it's nice and shiny. It should be shiny wire, not something that's dull and gray. And the trick is, now that I've actually got it done and cut, sorry, I don't know how well this is in focus. Afterwards, I can go back and I can trim it and make it the right length. And also, this is hard to see, but if I do trim it, I should see that the solder goes all the way through the wire, not just on the outside of it, which is more of a problem with larger gauge cables. So what I'm going to do next, again, I'm going to pretend this is some telemetry wire, something like that, that I'm going to want for my solar car. I'm going to pick an appropriate size piece of heat shrink. This is not appropriate because it doesn't fit over it. So let's get something slightly larger. You can always trim your heat shrink. You don't need to use the full length of it. So let's just do that. Important that you put the heat shrink on, because otherwise you have to cut this apart and do it again. You also want to be careful about putting heat shrink on hot things because it'll shrink on you before you intend it to. Now I'm going to get my little connector. I'm going to slip it over the top. Notice it's a pretty loose fit. And where'd my crimping tool go? I'm going to use this, which isn't necessarily meant to crimp this, but it will get the job done. So I've got my wire in there. I'm going to just crimp this real quick, give it a nice, see? And my wire didn't actually stick in there. So let's try that again with a bigger one. If you guys can't tell, it's been about 2 years since I've actually soldered a wire. But these skills, like riding a bike, never fade. Okay. Let's see if I can get it this time. If not, I'll have to use the bigger one. Yeah, it's still not ideal. Actually, this will be a good learning example. There we go. Okay. Now I've got it squished in there. Now it's on there kind of snug. I can't actually pull the wire out. So I could leave it like that, or I could actually take and do the last step. This is what we did on my team. You're going to want to pull the heat shrink back a little bit. And I'm actually going to go ahead and put a little bit of solder on this. Notice my tip of my soldering iron has gotten kind of oxidized. Fun part of soldering iron, don't flick it at your friends, but I actually just take it and flick it like that to get rid of the solder. And so what I'm going to do, again, get some bright, shiny solder on there. Solder is what conducts the heat. There we go, touched it. Now you can see that I've actually gone in there. I've heated it up enough that the solder's melted to the wire and it's kind of melted around the ring. This will never come undone, and this will be a very, very low resistance connection. Now I need to wait till this cools down. Let's see, test it with fingers. That's still pretty dang hot. Yeah, this is why I can do this with my fingers now, because I spent my high school years touching things that are way too hot. All right, I'm going to slip the heat shrink over it. See, I should have used a slightly bigger size of heat shrink, but there, I've got it on there. And my last step is to get my noisy heat gun here. Just flip it on real quick. Let's see, wait for it to start getting hot. Then let's see if we can see it shrink. There we go. So I'm just going to move it up and down, and now we can see that it shrunk around the connector. Be careful where you set your heat gun down so you don't actually set the trash on the floor on fire, and that's it. So, I mean, this was a super quick tutorial on how to do this. The main takeaways I want people to realize is tin the wires beforehand, and if you do something like this, it's not going to fail. Whereas you saw, when I thought I had the thing crimped in the beginning, the wire just fell out. And that's a common problem on solar cars. You get a marginal crimp and it leads to unreliable systems on your cars. If anybody is more interested in this stuff, I'd be happy at some time. I mean, it's hard because we're virtual right now, but to try and talk people through it or do something a little bit more in depth with better cameras. All right. Are there any questions about that now?
Well, Chris, Thank you for your presentation. I think it was great to be able to understand both the theory behind the electrical stuff and then also this hands-on demo, and hopefully people can go back and refer to it afterwards.